Hello everyone, now I am going to explain emissivity measurement apparatus. First of all, aim of this experiment is to determine the emissivity of the given surface. For that one, before going to the experiment, what is meant by the emissivity? Emissivity is the ratio of emissive power of a test plate to the emissive power of a black body. Here emissive power of a black body is 1 because the black body emits total radiation or absorb the total radiation. So that's why the black body of the emissivity is 1. So other surfaces other than the black body, the emissivity of the remaining surfaces is less than 1. For that one, this is the experimental setup of the emissivity measurement apparatus. This is the closed enclosure and two bodies are placed here. One is the black body and another one is the grey body. This is the black body and this one is the grey body. Two bodies are placed here and the power supply is given individually to the black body and the grey body. Two bodies having the same diameter and same thickness. Two heaters are provided to the individually provided to the each body to give the heat supply. Initially we are giving the electrical energy to that body. This electrical energy is converted into the heat energy by using the band heaters, and one console switch is provided to the panel, and from this console switch the power is distributed throughout the panel, and after that two heater switches are provided. One is for the grey body, another is for the black body. Two dimmer starters are provided to the panel. One dimmer start is used to control the power of grey body and second one is used to control the power of the black body. At the time of giving the power to the each two bodies, you have to maintain some small difference between the two bodies. Here you provide a little bit small amount of high power compared to the grey body, because black body will absorb the high amount of the heat energy. That's why you have to give the high amount of the power compared to the grey body. At the same time, at the time of calculation the emissive power or emissivity of the grey surface, you have to maintain the both body temperatures having the same temperature. If you are not maintaining the same temperature, it is not possible to compare the emissivity of the other surfaces, I mean non black body surfaces. So I am go with the experimental procedure. I am switch on the equipment, switch on the console first of all, so the energy is distributed throughout the panel, and switch on the heaters of both black body heater and the grey body heater here, and give the power and show the some difference between the two powers. This one is the power indicator of grey body and this one is the power indicator of black body, and this one is the temperature indicator and the channel selector. Here T1 shows the temperature of the black body and T2 shows the temperature of the grey body, and T3 shows the ambient temperature surrounded by the two bodies. Three thermocouples are placed inside the chamber here. Observe here the temperature is varying with time, 143.7, 9, 8, like that. The temperature is varying second to second because it is in unsteady state position. So you have to wait the steady state condition is reached. When it will reach, the temperature does not change with time. So you have to wait up to the temperature reading changes. And one thing you have to understand and keep in mind while calculating the emissivity, two bodies, grey body and the black body, having the same temperature, and if you are not maintaining the same temperature, it is not possible to compare the emissivity. Repeat the experiment 10 minutes. After the 10 minutes, wait for the 10 minutes, take the readings for this one, and after reaching the steady state, you can go for the calculation part. Please record the values here. W1 means the power given to the black body, that is 83, and 76, that is power given to the gray body. T1 is the temperature of, surface temperature of black body, that is 163.4, and T2 is the surface temperature of gray body, that is 141.9, and T3 is the 45, that is ambient temperature within the enclosure. Still steady state is not reached, you have to wait some more time. Take the readings after the 10 minutes. 170, T1 is 170, and T2 146.8, T3 45.2. Again the temperature is varying, and the both temperatures, both body temperatures are not equal, so you have to wait some more time. Again take the readings after the 10 minutes. I am keeping the power is constant, not varying the power, and temperature values T1 is 173.3, and T2 149.3, and T3 45.3. So still some variation is there between the T1 and T2, you have to wait some more time up to the both temperatures having the same temperatures, both bodies maintaining the same temperature. So after the 10 minutes I am taking the readings 176.4, 154.3, and T3 46.4. Still the steady state is not reached here, because the difference between these two is here. Again and again I am taking the readings, within the some certain time gap. So finally the steady state condition is reached here. The temperature variation from before the 10 minutes and after the 10 minutes, the variation is not there. At the same time the body, both black body and gray body maintaining the same temperatures, almost same temperatures. So then I am going to the calculation. So here these are the final values after reaching the steady state. So I am going to the calculation part here. In this W1 means heat supplied to the black body, and W2 means heat supplied to the gray body, and T1 and T2 are surface temperatures of black and gray bodies, and T3 is the ambient temperature within the enclosure. Epsilon is the emissivity of gray body or test plate, and EB is the emissivity of black body, and sigma is the Stephen Boltzmann constant, and its value is 5.66 into 10 power minus 8 watt per meter square Kelvin power 4. So these are the variables, and we know that heat given to the black body is sigma A epsilon T1 power 4 minus T2 power T3 power 4, and heat given to the black gray body is equal to sigma A epsilon T2 power 4 minus T3 power 4. Here I am subtracting from black body to the gray body, heat given to the black body to the heat given to the gray body. Here I am subtracting from heat given by the black body to the heat given by the gray body, equal to, here sigma is the constant and it is the same for the two equations, and area is the constant for both conditions because the diameter of the both bodies having the same. So sigma A, and temperature is the same because T1 is equal to the T2. Observe here, T1 is T2 almost the same, T1 and T2 values are almost the same, and so that's why T1 minus T3 emissivity of black body minus emissivity of gray body. So that implies emissivity of gray body equal to W1 minus W2 divided by sigma A T1 power 4 minus T3 power 4. We know about that emissivity of black body is equal to the 1. So emissivity of gray body equal to 1 minus W1 minus W2 divided by sigma A T1 power 4 minus T3 power 4. So substitute all the values, related values in this equation, W1 and W2 sigma area. Come to the temperatures part, you have to substitute the temperatures within the kelvins because the Stephen Boltzmann constant value is in kelvins. You have to convert this value either in degree centigrade or temperatures in the kelvins. In our point temperatures, converting the temperatures into kelvins is easy. That's why convert the temperatures degree centigrades into the kelvins, and we substitute all the values in this equation. Convert the temperatures into Kelvin. T1 equal to 176.8 plus 273 449.8 Kelvin, and T2 equal to same, and T3 equal to 46.7 plus 273. T3 46.7 plus 273 319.7 kelvins. So substitute all the values here. 1 minus 83 minus 76 divided by 5.66 into 10 to the power of minus 8 into area pi divided by 4 into 0.15 square into temperatures 449.8 power 4 minus 319.7 power 4. That equal to finally we will get 0.6 77 as the emissivity of gray body, which is less than 1. So the value of the emissivity of the gray body is 0.77. Okay, thank you.